Okay, the following is designed to give you just a few hints on this homework problem for number 2, which usually gives students some difficulty. For the first part, where it asks, the situation is we have a motorboat that is heading due west at 10 meters per second in a river that has a current of 6 meters per second due south. So it's probably best that you draw a picture of this situation. In this case, here is the river, and the motorboat can be drawn as it's heading due west. So from above, there's your motorboat. Now it's heading due west with a speed of 10 meters per second. So if you were to draw that as a vector, it'd be in the western direction, and of course you'd give yourself maybe a compass so you can understand what direction is which. And it would be with a velocity of 10 meters per second. And at the same time, the river has a velocity of 6 meters per second due south. And we could draw that like so. 6 meters per second due south. In fact, I'm going to draw that just a little bit shorter, because if I want the magnitude of my vector to be indicated by the length, then I should do that. Now, to give you a hint on this, what I want you to realize is, well, just these are both velocity vectors, so you can add them tip to tail. And now what you have is two vectors with a resultant, well, that looks like this, down and to the left. From here, you should be on good footing to solve for the resultant velocity of the boat. And I'll give you a hint. There's probably some old dead white guy who's screaming out to try to help you out here. For the next part of this problem, where it says if the river is 2.0 times 10 to the 2 meters wide, which if you translate that by converting, it's actually 200 meters. It wants to know how long does it take for the boat to cross the river. Well, by asking how long, they're asking for the amount of time that it takes to cross the river, and of course by giving you the fact that it's 200 meters wide, they're giving you the distance that it travels. But here's the hint. That distance that it travels is only the distance wide of the river. And if you were to break this down into, say, an X and a Y view, then really they're talking about the distance in the X direction. Now, if you had, from part A, written down the velocity vectors, that is, the vector that was pointing west, and then the vector that was pointing south, indicating the river's velocity, then you probably got a resultant vector that was down and to the left, or southwest rather. I think what most of you are going to make a mistake on here is you're going to try to use this distance here, or you'll use the 200 meters, but you will try to use the resultant velocity that you got in part A. This is where people often make this mistake. I want you to realize that the angle that the boat is displaced from its original direction, due west, is the same for the displacement and for the velocity. But, like I said, when you make a triangle of vectors, you cannot put a resultant velocity on the same triangle as something with displacement. They have to all be the same type of vector. So, when you're making your triangle, what I want you to realize is that the displacement in the horizontal direction is completely independent of the displacement in the vertical direction. And so is the velocity. So if you're heading toward the west at 10 meters per second, because we got that from part A, and if the river is 200 meters wide and you're traveling at a speed of 10 meters per second, well, your velocity in the horizontal direction, which I'll label as Vx, only relates to your displacement in the horizontal direction, which I will call dx. Now, if you take this information and you go back to stuff that you already know from a way long time ago, then you should be able to solve for how long it takes to get across the river. So the big key here is to realize, yeah, you are moving with some resultant velocity, and yeah, the river is also taking you down at a particular velocity, but the fact that the river is only 200 meters wide in the horizontal direction, and that you're only moving at 10 meters per second in the horizontal direction, this is really all the information that you need to solve this. For this last part, C, it wants to know how far downstream is the boat when it reaches the other side. Now, this is, again, pretty confusing, because if you take a look over here, what you had from part A was a right triangle with a vector of 10 meters per second to the left and a vector of 6 meters per second down, or 10 to the west and 6 to the south. And you ended up getting a resultant velocity that was southwest. The same triangle that you used for part A and perhaps for part B, you can use in this instance. But the only thing that's going to carry over from triangle to triangle is this angle right there. Both of these will have the same angle between their vectors and the resultant. But you will not be using meters per second, that is a velocity vector, on the same triangle as a displacement vector. So that's very important for you to realize from the beginning. Okay, there's actually two ways that you could solve this part. If you realize that from part B, you had found a time, the time that it takes to get across the river, widthwise, you could use that time and realize it's the same time that it would take for you to move in the vertical direction as it would be if you were to move in the horizontal direction, as it would be for you to move along your resultant direction. The time that it takes to hit the other side has to be the same in all of those cases. So you could use this time and now use your velocity in the vertical direction, which I'll call Vy. And you could use this equation. Your velocity in the vertical direction is equal to your displacement in the vertical direction divided by the time that it takes, which is the same. That's why I'm not going to give it its own direction. And then you can solve to get this guy all alone. You could do that. Or you can make a new vector triangle, but this time, instead of drawing a velocity vector triangle like you did for part A and for part B, you can now draw a displacement vector triangle where you already know the horizontal component of that triangle. It's 200 meters. That's what they told you in part B of this problem. Now, if you wanted to go this way, which is a little more difficult, but you can still do it, you could find the angle from your velocity vector triangle and realize that it's the exact same angle that would be part of your displacement vector triangle. In other words, you can use trigonometry to find this angle. Realize, I'm going to change up some ink here so you can see what I'm doing, that if you want to find this angle, you already know the side that is opposite and you know the side that is adjacent. And if you've done part A, then you also know the side that is the hypotenuse. But just given this information, the fact that you have your adjacent side to that angle, because it's right next door to that angle theta, and you also have your opposite side because he's across the street from your angle theta, then you could use adjacent and opposite. I wonder what those two relate to in terms of the trigonometry functions. Well, Tom's old aunt sat on her cat and hollered. The only one that deals with both the adjacent and the opposite, when you know them, is the tangent function. So you could use the tangent function to solve for this angle. And then once you solve for that angle, you can now use that same angle here and break it down to find this displacement. Because that's what they want to know. How far downstream have you gone? In other words, what is your displacement in the vertical direction? We already know the displacement horizontally, and now we want to find the vertical displacement. So you can find that angle by doing this. The tangent of the angle is equal to the opposite side, which is 6 meters per second, divided by the adjacent side, which is 10 meters per second. And if you run that through your calculator, the tangent of this angle ends up being 0.6. So if the tangent of the angle is equal to 0.6, then if you go to your calculator and there's a button that says second function, and then hit the tangent button, you will find that the angle is just about 31 degrees. So you now know that this angle is 31 degrees, and you know the adjacent side. Now if you're looking for the opposite side, you know the adjacent and the angle, and you're looking for opposite. Okay, opposite, you have adjacent, and you have the angle. You can now use the same trigonometric function, but instead you're going to insert your values for your displacement vector triangle. So if the tangent of an angle is equal to the opposite divided by the adjacent, you already know the angle. It's 31 degrees. And if you know the opposite side, you'd be done. That's what you're looking for. It's the vertical displacement. And if you know the adjacent side, which you do, you can plug that in. So tangent of 31 is equal to the opposite side divided by 200 meters. This is the guy you're looking for. So to get them all alone, you multiply both sides by 200 meters. That cancels out. And you come over here, and 200 meters times the tangent of 31 degrees should get you your answer.